All right, so next section of chapter 4 here. Talking about curve sketching. So what we've done so far in chapter 4 is basically how to get a bunch of data about what a curve looks like and how it behaves. Now we're going to bring all that together and get some, instead of like really rough sketches for curves, include a lot more detail than we were able to before. So here's some things to look at when we're looking at curves. So domain. So basically what x values belong to the function we're looking at. So it's probably easier to talk about domain in terms of when the function is not well defined. So what kinds of things can cause a function not to be defined? So yeah, division by 0. Anything else? Yeah, take it. So I'll say even root of a negative, because it's not always square roots, could be like a fourth root or something. Oh, yeah, so taking the even root of a negative number, that gives you something that's poorly defined. There are others that we've seen. These are the two major ones to look out for. Intercepts. So where does your curve cross the x and y axis? If I want to find an x-intercept, how do I find those? Not where x equals 0. If I'm looking at a function of right. So if you're looking at where the graph crosses the x-axis, that's y equals 0. Y-intercepts happen when x equals 0. Symmetry, something we haven't talked about. Hopefully you've seen this. It might be a little two of the major kinds of symmetry. So we'll give you a couple different representations of each. So even symmetry, basically, if you can take everywhere where x shows up in the definition of your function, if you replace it with negative x and nothing changes, you're looking at an even function. Example on the left of an even function, because if I'm taking negative x values and I get the same values as I would get when the function is evaluated at those positive values, you're getting symmetry. How can you describe the symmetry that's going on in this even function? Yeah, it's over the y-axis. So that's one thing you'll see with even functions. This one right here is an odd function. Basically, every time I take the opposite of x and plug it into the function, that's equivalent to me just taking the opposite of the y value as well. So on the right, you're seeing an odd function. That was a little more subtle. How would you describe the symmetry on something like that? It's rotational about where? Yep. So yeah, if you take your function and take a half turn about the origin, you will get the same. Graph. So graphically and algebraically, those are how those functions are represented. How are we doing so far? Other things to look at. Periodicity. Does your function repeat? What are the quintessential examples of functions that act like this? Good. Sine and cosine, really all the trig ones are periodic in some way. This function is not obviously a trig function, but it is periodic. Asymptotes. Where do vertical asymptotes come from? What is it about a function that causes a vertical asymptote to exist? What do you mean by X being undefined? Right, okay, that's better. So yeah, X itself is, it's hard to think of that as being undefined, but I'll say this, at X values, not in domain. And I'll say here, maybe. Because there are examples where X is not in the domain where asymptotes don't show up. Probably the easiest example to look at here is, what if I said, all right, this X value, I just pluck that out of that function. But those are the things we typically look for. What X values is this thing not defined for? Another way that we've represented this in the past is, if you have this, the limit as X approaches some points of your function is equal to plus or minus infinity. So basically, as you get really, really close to some X value, your function either increases without bound or decreases without bound. That's a little more precise way to think about. We've also talked about horizontal asymptotes. Where do those come from? Kind of a similar idea. No, so for example, that's kind of what this is right here. This thing I just drew. That's removable discontinuity, but that's more like a vertical asymptote.
Okay.
In fact, and it's kind of weird. Like let's think about a function that has horizontal asymptote. Probably the easiest one to think about is 1 over x. And it's nice because it has both. What's the horizontal asymptote of the graph I just drew? Y equals 0 or the x-axis, same thing. So is there a way we could express that in the language of limits? Yeah, so I'll generalize it like this. So the limit as x approaches either, so now we're looking at x getting very large or very small. And if there's a horizontal asymptote, what is the function getting close to? For the function I just drew, it was 0, but I can have horizontal asymptotes that are not 0. So I'll just say C. So if you have some limit as x goes to positive or negative infinity, if that is some real number, any questions so far? I feel like I walked in here in a rush, so if I'm going too fast, tell me to slow down. All right. Intervals of increase and decrease. Hopefully by now you have a good idea as to how to look for this kind of thing. How do you find intervals of increase and decrease? Let's just start with increase. Sebastian? Plotting what? Right, so positive, yeah, so it's about something being positive and negative. What that something is really important. The slope, how do I get the slope? Which derivative? Yeah, so I mean, I know it feels like I'm nitpicking you, but if f prime is greater than 0, what does that mean? That's an increase, right? And since I'm hammering you all for being really clear about stuff, this means that f is increasing, right? So if you want to know whether f is increasing or decreasing, most direct way to learn that is through the first derivative. How about local minima and maxima? Where do those happen? Okay. Do local minima and maxima have to happen at critical numbers? Let me say it this way. If I have a critical number do I have an absolute local min or max? Maybe, right? So I'll say this. Here's the thing though, if I have a local min, is that a critical number? Okay, that much is true. Local minima, maxima may happen as critical numbers. So we know that critical numbers are important because that's where these things might happen. What else do I need to look for though? I got a critical number, so the derivative is either 0 or undefined. What else would really tell me if that point is a local extreme of some kind? Not inflection point, because that's something a little different. Oh, I think I know what you're getting at. That. Right, how do we find that change of direction? Yeah, so if f prime is less than 0, let's say critical numbers are called C. If f prime of C is equal to 0, and I'm struggling with the right way to say this precisely. F prime of C minus epsilon is less than 0, and f prime of C plus epsilon is greater than 0 for some, I don't care what epsilon is, as long as it exists. Actually, I don't like that either. I'm going to go back to the definition we said long ago. So if f prime of C equals 0, and let's say we're going maxima, right? If fc is greater than or equal to f of x for all x on this interval, C minus epsilon, C plus epsilon. I'll stop there for a bit because I think that might be a little serious. Do I need to draw a picture of this? Man, I know we've used this definition before, but it's been a while, and I'm not going to assume that it landed without a doubt there. So let me show you. Here's a really simple function with a local maximum. Let's say this point right here is 1, x equals 1. What's a good epsilon I could choose to meet this criterion for local max for me? Well, I need epsilon to be positive. I think, are you saying that 0 should start this interval? That would work. Yeah, if I make epsilon 1, then if I'm just looking at this little narrow band here that's like 2 units wide, is f of 1 the highest thing there? Okay, that's a local max. Doesn't mean there are lots of epsilons I could have picked. But so long as you just need to be able to choose one where I can say everything inside that window is no higher than the middle of it. We okay with that? Sort of. Got a question? Cameron?
So the critical value thing only applies to local.
No, so it applies to both.
Oh, okay.
But I was trying to make a definition for, so let's say this. I mean, this definition I wrote was for maxima, right?
Yeah.
But I can make it work for minima if I just make a couple of modifications, right?
Yeah, so you have the FFC is listener.
Yeah, so yeah, I can basically, that right there covers both definitions now with that one little modification. Yeah, C is the value of what variable, X or Y. Yeah. So the C is the critical number, F of C is the extreme. Whatever the Y value is at that at that x value. Concavity. How do I find out if my function is concave up or down? Let's just start with that. How do we do if my function is concave up? What does that tell me about the function, or it's one of its derivatives, or anything at all? Not the third.
The second.
Yeah. I haven't tortured you with the third derivative yet. I promise you I won't this semester. So yeah, the concave up means that f double prime is positive. What can I say about f prime, f single prime? I think this is really important, because I think the first question on the homework last night. Because you were asked things about the concavity of a function, and all you had access to was the graph of the first derivative, right? So how did you tell, if you had a graph, so you had a graph of the first derivative, how would you tell concavity from that first derivative? Sebastian? I think if you have a graph of f, that'll work. I don't know if that'll work as well with a graph of f prime. Let me ask this question. How is the second derivative of a function related to its first derivative? Not if it's positive or negative. Tells you if it's increasing or decreasing, right? So, and I could have asked that question in a different way. What does the ninth derivative of a function tell you about the eighth derivative of a function? But the ninth derivative tells you the rate of change of the eighth, right? And that's how all derivatives work. So if you're looking at the derivative, sorry, let me say it this way. If you want to know something about a function, you just need to take its derivative, right? Doesn't matter what that function is. So in this case, if I'm asking about the derivative f prime, kind of like you were in the first question, the homework, f prime is the first derivative of some other function, right? Some parent, base function. The second derivative is the first derivative of that function, right? So the way those two things are related is the same relationship as between f prime and f. So it's basically how many orders of derivative are you looking at here? Which is kind of a confusing way to think about it, but I think that unity is a really important thing to get a handle on. Because let's talk back about increasing. I know that f is increasing if f prime is positive, right? So if f double prime is positive, what does that mean about f prime? Not f prime. I can tell you that f is concave up. F prime is increasing. So f being concave up. In fact, why don't I write these in a different order to show kind of like it's a chain of these things. F being concave up, that says this about f prime. It's increasing. And we did this exercise on Monday where we had, I gave you a graph of f, drew a bunch of tangent lines. And if those tangent lines were decreasing. So if f prime is increasing, what does that mean that f double prime? What must be true at f double prime? It's positive. I don't know if it's increasing or decreasing. I just want to figure the zero at that. If I wanted to look at f triple prime, what would I know about it? I don't know. Yeah, so there's a point where concavity is one of the, so Increase and decrease is something that tells you about the first derivative. And no but. Concavity is a thing that tells you about the second derivative, but no but. So I can use the second derivative to draw conclusions about f prime or f, but I can't. That's what I'm stuck with. I'm feeling like the water's got a little muddy. Are we okay, or do we need to pause and get some questions answered? All right, so let's start compiling that information together to figure out this curve here. So I think the first thing we talked about, we're trying to get data to sketch a curve, is the domain. Are there x values where this function would not be defined? How do we know 1 and -1? So if I set the denominator equal to 0, I get that x is equal to -1 and 1. Does that mean that those are there? I'm going to have vertical asymptotes there. I can. I don't know yet, but I might. All right, so we know the domain is this. We'll just write it in set builder notation from -∞ to -1, -1 to 1, 1 to infinity. All right. I mean, the next thing we looked at was intercepts, right? Let's start with the easy one. Am I going to have a y-intercept? Where is it? At the origin, right? Which means I also have an x-intercept at that point. How do I know? Good question. Plug in 0 for x. So basically what I'm looking for is, x equals 0 means that y equals 2 0 squared over 0 squared minus 1. Is it possible to have many y-intercepts? See a nod for yes and shake for no. The person who voted yes is now voting no. You cannot. How come? I mean in general. In general, can I have many y-intercepts? No. Right, it's a function, right? So think about what it would look like if you had many y-intercepts. That means you said x is equal to 0 and y equals 2 different things. That's not how a function can look. So we got a single y-intercept. Can we have multiple x-intercepts? Yeah, that's possible. Do I have multiple x-intercepts here? What do I have to do to find x-intercepts? So if I say that 2x squared over x squared minus 1 equals 0, that's equivalent to 2x squared equals 0, right? Yeah, I'm not going to get another one. So I believe I have a single intercept that goes to the origin. So I got my domain. I got my y-intercept. We can look for symmetry if you want. Do I have some kind of symmetry here? What kind? How do you know that? That's exactly right. So think about like kind of the algebraic way to look at even symmetry. And let's test that. What is f of negative x going to look like? 2 times negative x squared over negative x squared minus 1, which is the same as 2x squared over x squared minus 1, which is what the original function was. So that's really helpful because basically if we can graph half of this function, we can just mirror it. It's going to be reflected over the y-axis. All right, so we got intercepts, we got domain, we got some kind of symmetry. What else is good to look for? You can look for asymptotes. So let me start partitioning this. I'm going to say let's look for horizontal asymptotes first. So what's the limit as x approaches negative infinity? How'd you get 2? Right. Right. And if we want to show that algebraically, remember I can multiply both top and bottom of this thing by 1 over x squared. And it's the same. So that'll give me 2 over 1 minus 1 over x squared, which is 2. Yeah, so, well, I mean, yes and no. I think that's why, that's how this change right here is the limit. So limit. So I'm not allowed to break up the small. But if I divide the whole thing by x squared, you write it down. So this limit exists. I have 3 limits that exist. And I can just break them down after that. What do we think the limit as x the limit is as x goes to positive infinity? Why? How do you know it's 2? Because of the symmetry. So, and the limit as x goes to infinity of f of x equals 2, because even. Function's even. Can I look at vertical asymptotes now? Where might a vertical asymptote be? Cameron?
Well, it would be when the denominator equals 0 because it's dependent on it. So we already have that in the domain. So they would most likely be a -1.
Right. So I need to look at both.
And-
I can actually get away with only looking at one. How come?
Oh,
Because of the symmetry. If I figure out something about x equals what happens when x approaches 1, then I've learned all I care to learn. So the limit as x approaches 1, and we should do from the right just to make it easier to think about one piece at a time. How can I find this limit? Can I use L'Hopital's rule? No, that's not allowed. What else can I try? It's one of those times where you can, it's okay to kind of reason your way through it. So I want x to approach 1 from above, right? What's going to happen to the numerator as x approaches 1 from above, from the right? It's going to get closer to 2. What's the denominator going to do? Going to get closer to 0, and it's going to remain positive, right? So your numerator is getting closer and closer to a finite real number. Your denominator is getting closer and closer to 0, but it's going to stay positive. So what's the overall thing going to do? Go to infinity, right? I think I found an asymptote. We should also look at what happens when on the left-hand side, Would you agree that that's negative infinity? Is the denominator, and the real thing you have to look for is this: is the denominator going to be positive or negative as I approach from the left? If you have a number that's less than 1 and you square it, is it still less than 1? Yes. So I believe, yes, the denominator is going to be negative. So we could look at derivatives, but I think I have enough information with this one. So let's try it. We know we have what values are not in the domain? -1 and 1. I know that I have vertical asymptotes at both, right? Even though I didn't look at both. And I know that as x approaches 1 from the left, I'm going towards negative infinity. And as x approaches 1 from the right, I'm going towards like that, right? Where did we say that I had horizontal asymptote? +2, right? So maybe I should graph that before I start trying to plug in the curve. So I feel pretty secure about that. And because the function's even, what happens? Because the function's even, I should feel pretty secure about that. I know I have. The only place I cross either of the axes is at the origin, right? What other information do I have? I don't know if I know enough about what's going on in the middle. I feel like I have a good idea what's going on at the left end and the right end. Does that make sense? But what other information should I try to get to figure out what's going on in the middle? Yeah, let's do derivatives. You guys mind if I get a fresh screen out of this? Okay, so first derivative is going to be what? You can't just take derivative of both. So I'm got to go through the motions of quotient rule. Does this simplify at all? 4x cubed minus 4x minus 4x cubed. That's kind of nice. So what can I do with this derivative now that I have it? Can find places where it's equal to 0. That's just 0, right? So we have a critical number at our intercept. That actually might be really valuable to figure out what's happening on either side. So where is y prime undefined? Y prime undefined at, right? And that's going to be at x equals -1 and 1. Which hopefully we expect because the function's not even continuous there, so its derivative shouldn't exist there. So we know something about we got a critical point. So how can we learn more about this critical point? The line thing, trademark line thing. So x values, I'm looking at f prime. I only have one critical value. What are some good x values to use? And those are both going to be problems. Yeah, so, and here's the other thing. I can't use -1 and 1. Could I use -2 and 2? And those are also bad. I gotta stay between my critical numbers because I know my derivative is 0 here, undefined here, undefined here. Let's say you find out something about the derivative at -2. That actually doesn't tell you anything about what's going on around 0. So I really got to stay between my critical numbers. Oh, no, it's not what I wanted. So what is the derivative equal to when x is equal to -1/2 and +1/2? Go ahead. Yes, it would, but I kind of already know that because I know something about horizontal asymptotes. Yeah, absolutely. In fact, yeah, if we want to do that, we can do that too. Let's be completionists. It's all good. So if I want to test those points, if I plug in -2 to my derivative, I should get 8 over something positive, right? 8 over 9? Yeah, 8 over 9. How about -1/2? That's going to be 2 over. I'm just going to say positive. Okay, if I make that shortcut. Is it clear that the denominator is going to be positive all the time? Okay. So that just means I need to look at the numerator, which is going to be negative all the time on the right-hand side of 0. So what did I learn about my critical point? So I have a local max at where? 0, 0. Do I have any other local extreme points? Because of this information here. Oh, I'm so glad you asked. So I'll try to recreate some of the things we already learned. So from -1 to 1, we have a good idea, right? Actually, no, that's where we were kind of lost. We had a good idea what was happening outside of that range. We have a horizontal asymptote at x equals 2. And I had a pretty good idea that this was going on, right? And now we know that this intercept is a local max. So what do we know about the way this thing behaves in the middle? It has to go down, and is it possible for this thing to come back up? Why is it not possible? That's one way, but how do we know we have no local maxes like inside this like middle structure? We proved they don't exist. So, in fact, I don't like the way I started this. This slope really should be 0 here. So just by the way this graph like must be behaving, can I figure out the concavity from the graph now, or can I get some kind of sense of that? What's the concavity like on the far left? Middle. The slope can get infinitely small on the far left. And on the far right, concavity to the right of +1. concave up. But what's true about the first derivative everywhere? It's increasing, but it's never positive. So kind of just finishing, the increases, the first derivative is always getting larger, but it never reaches zero. It never becomes positive. So kind of a lot of things to do there. I think but I got a couple minutes left. Any questions on this? All right, I have a test for you if you're willing to stick around.